Hi everyone. In this video we are going to continue our discussion of eigenvalue problems and get into the topic of Fourier expansions. These are very special ways to represent functions so that we can solve more interesting differential equations such as the heat equation or the wave equation. So let's get to this and take a look at what we can do here. So we're getting into Fourier expansions. So let's review what we talked about last time, the eigenvalue problems. Okay, so we worked through in detail problem 1, where we were looking at this differential equation, and we discussed how this is an eigenvalue problem, where lambda is the eigenvalue, and the solutions to this equation are the eigenfunctions. All right, so refresh yourself on that last video if you don't recall what we're talking about. And this is going to be a boundary value problem where we are specifying the values of our function at the boundary of some interval, the interval from 0 to L. Now, I left as an exercise for you problem 2 to investigate the solutions to this differential equation where we have slightly different boundary conditions. Here, instead of defining the value of the function at the endpoints of our interval, we are specifying the value of its derivatives at the endpoints of the interval. And we have other problems as well where we change up these boundary conditions. And the last one, slightly different, we aren't specifying that the conditions be anything in particular. We're just specifying that the conditions are the same at the endpoints of an interval, and this interval goes from negative L to L instead of 0 to L. So just to illustrate what we're doing here, I keyed up something in Desmos, and here is the first problem 1 type of boundary condition, where we are insisting that the function be equal to 0 at the endpoints of the interval. And now my interval just goes from 0 to 1. So in these examples, L will be equal to 1. But it could be any positive number, really. All right, so the type of solutions that we're looking for in problem number 1 are the type of solutions that are pinned down. They have to be equal to 0 at 0 and at L. So you can see there's all these. I'm just showing you some possible functions here, but you know the requirement is that the function needs to be pinned down at those endpoints. The boundary value problem number 2 was just saying that the derivative was equal to 0 at the endpoints. So you can see it's not fixed at any particular value at the endpoints, but the derivatives are equal to 0, right? And you can see that in these graphs here. Just examples again. And the third boundary value problem had the function fixed to be 0 at 0, and the derivative was 0 at L, but it doesn't say what the value of the function was at L, so that can change. Although in these examples I have it fixed, just because there's just a limited number of examples I can produce here in a finite amount of time here. But you can see that the derivative is 0 here, and the function value is 0 here. And then in problem number 4, we had the reverse, right? We had the derivative was 0 here, and then the function was equal to 0 over here. You can see there's lots of different functions that can do that, right? And then finally, the last boundary value problem, where we went from negative L to L. So here I'll go from negative 1 to 1. Examples of functions that might satisfy that look like this. So see what's happening here. I'm not specifying what the value of the function is at the endpoints, right? It could be a lot of things, but I am saying that whatever it is over here, it has to be the same value over there. So if it goes up on the left, it's got to go up the same amount on the right, right? And the derivatives have to match, right? Notice the derivative here matches the derivative there. Now, one of the interesting contexts in which this makes sense is that if we were actually imagining this interval as wrapping around a circle. So if we took this interval and wrapped it around and made a circle, we would want a function that would not have any kinks or discontinuities in it. And so at the endpoints of this interval, the value of the function and its derivatives should match up so that as you go around the circle, you don't have any discontinuities or anything like that. So that's one application of this, is if we were going to define something actually on a circle. But anyway, those are the different boundary value problems that we can look at. And just to further review what we talked about last time, this is what we proved in the last video. The eigenvalue problem for the first boundary value conditions. And we proved that it had infinitely many positive eigenvalues. So these are all the different possible values lambda can be, and they're all positive. And the eigenfunctions, the solutions that go along with those eigenvalues, are given by this. They are all sine of some integer n pi x over L. Remember, L is just the length of the interval. And it says that's all the eigenvalues. That's all there are. So we've solved the eigenvalue problem. We found all the eigenvalues and all the associated eigenfunctions up to a scalar multiple. Remember, if you have an eigenfunction, any scalar multiple of that is also an eigenfunction. So you can only define them up to a scalar, a real number multiple. So you could multiply this on the outside by any real number you want, and it would still count as an eigenfunction. Okay, and then I left as an exercise for you in that video to do the other eigenvalue problem, problem number 2, where instead of specifying the value of the function at the endpoints, we specify the value of the derivatives at the endpoints. And you were tasked to show that this has eigenvalue 0 with associated eigenfunction constant 1, and it has infinitely many positive eigenvalues, same as before, with associated eigenfunctions, but this time almost the same, but this time they're cosine instead of sine. And that's all of them. There's no other eigenvalues. That's all the possible eigenvalues that this can have. And so it's interesting that all the eigenvalues have this particular form given by integers, positive integers n, right? Or n equals 0. It gives us the 0 eigenvalue. And if we skip ahead to the fifth eigenvalue problem, I'll skip problems 3 and 4. That was the one where the last picture we were looking at on the interval negative L to L. This one, if you solve this one, you'll see that the eigenvalues could be 0, in which case the eigenfunction is just a constant, and infinitely many positive eigenvalues, just like we had before. Again, they look like this. And the eigenfunctions here are either going to be cosine or sine. Right, so we actually have pairs of eigenfunctions. And that's all of them. There's no other eigenvalues. So that completely solves that eigenvalue problem. So what we're seeing here, if you solve the other problems, you'd also see the same pattern. We keep getting these same eigenfunctions. Right? So these are special functions for us. So this is what we're going to be talking about today. These special functions. And one of the things we're going to talk about is this concept of orthogonality. All right? Two integrable functions, and that just means that you can define their integral. Two integrable functions f and g are orthogonal on an interval if when you multiply them together and integrate, you get 0. And it turns out that the eigenfunctions that we were just looking at, we had all these different eigenfunctions from those eigenvalue problems. Those are all orthogonal. So in other words, if you take any one of these and multiply it by any other one of these and integrate on the in the interval negative L to L, you'll always get 0. And that's easy to prove using a little bit of calculus, a little bit of trigonometry. Very easy to prove. It's a really great exercise for you to do. I'm not going to prove it. It's proved in the book that we're using, but it's totally an exercise you could do. So all of these are orthogonal. Now, what is this idea of orthogonality that we're talking about? I mean, how can functions be orthogonal? Well, we know what it means for vectors to be orthogonal, right? We know that, let me zoom this in just a little bit. We know that two vectors are orthogonal if they are at right angles to each other. Right, so if I have vector v1 and v2, for them to be orthogonal, that means that v1 dotted with v2, I take the dot product, I get 0. Now, what does the dot product mean to do? Well, it means to take the components of V1, so that would be V1, 1 and V1, 2. I'm dotting this with V2, 1 and V2, 2. These are the components of V2. That means to take V1, 1 times V2, 1. So I just multiply these together. And then I multiply these together and add them up. And I'm getting 0. And if that's true, that means that these vectors are at right angles to one another. Okay, well, okay, so why does this make sense in terms of functions? Why can we talk about functions being orthogonal? Well, turns out you can think of a function as an infinite dimensional vector. Okay, so if I look at a vector, it's got components, right? It's got two different components. Well, I can think of a graph, right, where the first component is the value of some function above 1. So if my vector was 3, negative 2, my first component has height 3, and my second component has height negative 2. So I can kind of think of this vector as a graph. Okay? Now, why don't we make this a three-dimensional vector? If I had a three-dimensional vector, my third component might be 1. Okay, just to make it a little more interesting, right? So you can kind of think of this vector as a very, very rudimentary graph consisting of just 3 points. Okay. Now, if I take another vector, say I take another vector, and its coordinates are maybe 1, negative 1, 3, right? Actually, let me color code these. Let me use, no, that's not, that pen looked blue, but that's not a blue pen. It's a blue colored pen. Let's see, is this a blue pen? There we go. Okay, so there's another vector. Now, if I'm going to take the dot product of these two vectors together, I'm just going to multiply these, and add them up. That's what I'm doing. Right. Well, let's think about functions now. So functions, of course, have a graph. So here might be a function f, and here might be a function, that's the pen that looks blue, but it's not blue, doesn't write blue. All right, so here's my function, what was supposed to be blue, g, right? Now I can do the same thing here. I can, for every value of x, I can take the product of g with f, right? And then add those up, right? For every single value of x. Well, of course, if I add up infinitely many things like this, I'll probably get infinity as an answer. But we know how to deal with this in calculus. When we have to add up across an interval, what we do is we move to this idea of integral. So what we're going to do is if I want to take f dot g, what I can think of that as is the integral of f of x times g of x dx. This is like multiplying for each x the functions together and then adding those all up. And so a dot product extends to the idea, to the realm of functions as this integral. Now this notation is not really used in the mathematical literature. I'm kind of being a little creative here. However, there is notation for this. They actually use this notation. And they wouldn't call this the dot product, they'd call this the inner product. That's not important that we know that, but I just wanted to point it out. Don't go talking to a mathematician and talk about the dot product of two functions. They'll think you don't know what you're talking about. But if you say inner product, they'll know exactly what you're talking about. They may ask you to define which inner product you're using, and this is one of them. And this is the one that we're talking about. And this is the one that's analogous to how vectors work. And you can see that a function is like a vector except instead of only finitely many components, 1, 2, 3 components, it has a component for every x. So it's like an infinite dimensional vector. And so for two functions to be orthogonal, we say that this dot product, this inner product, this integral is equal to 0. And so that's the definition that we're using right here. Okay, so we mentioned that these eigenfunctions are orthogonal. Well, so what? Okay, well, when you have orthogonal vectors, here's something you can do. So let me take two orthogonal vectors. I'm going to call it phi1 and phi2. And they are orthogonal. They're at a right angle. And now I'm going to take any other vector, say v. I can write v in terms of phi1 and phi2. In some sense, I'm kind of using phi1 and phi2 as my new coordinate basis vectors. Ordinarily, we'd use the vectors that point in the x direction 1 unit and the y direction 1 unit. That's usual Cartesian coordinates. But what if I wanted to shift to a new set of coordinates? What if I want to use a coordinate vector that points at an angle like this and another coordinate vector that points at an angle like this? I want to use phi1 and phi2. How can I express v in terms of these vectors? Well, I do that by projecting v onto these vectors. So if I just project down at a right angle, what I'm getting is some vector that's parallel to phi1. So I'm getting some multiple of phi1. And if I project orthogonally onto phi2, I'm getting some other vector that is parallel to phi2. So it's a multiple of phi2. And so what I've done is I've written v as a sum, c1 phi1 plus c2 phi2. I've decomposed phi in terms of these vectors. So what we want to do is we want to do the same thing with our functions. Okay, so what we have is we have this infinite set of orthogonal eigenfunctions. So what we're going to do is we're going to take our function f and project it onto these eigenfunctions, just like we project v into these vectors. Well, how do we do this projection? Well, you should recall from multivariable calculus that to get this projection, there's a projection function. If you want to project v into the direction of phi1, or phi1 or phi2, I'll just write phi n, right? N could be 1 or 2. The formula for that is to take v dot phi n divided by phi n dot phi n and multiply by phi n. So this right here is my c. That's the thing that I'm multiplying by phi n. This is what I'll call Cn. So that could be 1 or 2. So if I want to get C1, I would make all these phi1s. If I wanted to get C2, I'd make all these phi2s. And so this is the formula that I could use, that we would use to get these constants. Well, that's exactly what we're going to do down here. If I project my function onto phi n, what that means to do is it means to, and again, I'm going to abuse notation and use this dot product notation, which most mathematicians will just not know what you mean by this, but we know what it means. We talked about it. It's the inner product. It's this. And how did we define this dot product? Well, we said it's the integral of f times phi n, and we'll integrate from minus L to L here. And then this is going to be the integral of phi n times phi n. That's phi n squared. And then we're going to multiply by phi n. Well, this right here is how we get our Cn. That's going to be a constant, right? That's going to be a number, because I integrate this, I get a number. I integrate this, I get a number. I get a number. So this is just going to be some multiple of phi n. So what we're doing here is we're seeing how much does our function f kind of point in the direction of phi n, or act like phi n. What's the contribution of phi n to our function? This is how much phi n contributes to our function. And we can do this for every n. For every phi n, we can find the degree to which it contributes towards f. And then we're going to use this idea. Just like we could write our vector as a sum of these contributions, we are going to write our function as a sum of these contributions. So we're going to write our function as C1, well, we're actually going to start with 0. C0 times phi 0 plus C1 phi 1 plus C2 phi 2. Now, we have an infinite number of these phi n's, right? So we're just going to keep going with this. And we get an infinite sum. And that is an infinite series that represents f. Now, I wrote a squiggly symbol here. Why did I do that? Why didn't I write equals? Well, because this series, we have to be careful. This doesn't always converge. And it can still be useful to consider it even if it doesn't converge. And so I don't want to say it equals f, but I do want to write it down. All right, so I need to put something here. So I put a squiggle. Sometimes this will be equal if the series converges, and it'll converge to f, hopefully. Well, more about that later. But this is called the Fourier expansion of our function f. It's the Fourier expansion of f. So that's what we're going to be doing here. We're just extending the idea from vectors. So, okay, so here are our eigenfunctions. So we're going to express f as a linear combination of those eigenfunctions. And we do that by projecting f onto each one of them. So C0 phi 0 is the projection of f onto the first, well, the 0th eigenfunction, 1. So that means that C0, let me make a little bit of room here, C0 is just this, right? It's the projection coefficient. It's the coefficient of that projection. Then we multiply by phi 0 to finish that projection off, right? Now, what is phi 0? Phi 0 is 1, so I can do this integral pretty easily, right? Just integrating 1 from minus L to L is, of course, 2L. So, right, that just simplifies to this. Now, this is an interesting expression here. Take a moment, see if you can recognize what nice way to describe what this thing is giving us in terms of f. Did you get it? Yeah, this is just the average of f on the interval minus L to L. So that's a really neat observation, that the first projection coefficient, first Fourier coefficient, the 0th Fourier coefficient, is just the average value of f on the interval. Okay, let's go to the next term. C1. C1 is just the projection coefficient of f onto phi 1. But what is phi 1? Phi 1 is cosine pi x over L. So here's an exercise for you. Integrate cosine squared pi x over L from minus L to L. What do you get? Pause the video, do that, work it out, okay? Let's check what you got there. You should have gotten L. It just integrates to L. So this whole thing just simplifies to this. So this is how we're going to express this piece. And then what about C2? Well, integrating from minus L to L of phi 2 squared, that's sine squared, that's also L. In fact, all of these are going to integrate to L, except for the 0th one. But all of these are going to integrate to L, right? So you can just simplify these coefficients in a very kind of nice way here. All right, so now what we're going to do is we're going to do one more thing. We're going to observe that these eigenfunctions are coming in pairs. Notice pi x, 2 pi x, 2 pi x, 3 pi x, 3 pi x, 4 pi x, 4 pi x. So they're grouped in pairs with a cosine and then a sine. So I want to group these coefficients in pairs as well. So we're going to rename these. C0 we're just going to call A0. And then we're going to go A1, B1 for the first pair. And then we're going to go A2, B2 for the second pair, and then A3, B3, etc. So we're going to rename them that way. And just to remind you, these phis are just these functions here. All right, so when we do that, we just get this. And so we can write that in summation notation as follows. Okay, so this is the Fourier series for f, where the coefficients are given as follows. And remember, these coefficients are just the projection coefficients that we get when we project f onto the corresponding eigenfunction. And just to reiterate one other point, this series doesn't always converge for every f. We need to check that, so do be cautious about that, checking whether this thing actually does converge to the function before you put an equal sign over here. Okay, so now what I want to do is I want to take a look at an example where we look at a specific f and see what happens. Okay, so here's the function I've chosen. I've chosen the function 1 minus x squared, and we're going to do this on the interval -1 to 1. So L is just equal to 1 in this situation. So let's compute that 0th Fourier term. Okay, the projection of this function onto the 0th eigenfunction, which was just 1. Right? So I had Desmos compute that. So you do that and you get this. And like we said, it's just the average value of the function. So this is just the average of our function on the interval -1 to 1. Okay? Now what happens if I project it onto the first eigenfunction? That was the first cosine that we saw. Well, I get something that looks like this. Okay? And if I project it onto the second eigenfunction, that was the first sine term that we saw, I get this. This is just, I don't know if you saw it here, just the line 0 appeared here. Now, why did that happen? Why are we getting 0? Well, if you look back here, our function, by the way, is an even function. It's 1 minus x squared. So we have an even function multiplied by an odd function. If you multiply an even function times an odd function, you get an odd function. Now, if you integrate an odd function from minus L to L, no matter what L is, you'll always get 0. So because we started with an even function, that b term is 0. And in fact, that's going to happen for every single one of the b terms, because every single one of the b terms corresponds to a sine, and that's going to happen. So for this particular function, because our f is an even function, all of the b's are going to be 0. And that's kind of a nice trick to think about when you're working on these problems. You know, if you happen to know ahead of time that your function is an even function, you could just ignore the b's. And if you start with an odd function, think about what happens then. I'll let you ponder that. Now let's look at the projection of our function 1 minus x squared onto the second cosine eigenfunction. I forget which one we're on, but it's the second cosine, all right? Cosine 2 pi x. So here we are, and that's the projection. And then what about onto the third cosine eigenfunction? We get this one, all right? I'm ignoring the signs because, like I said, those are all just become 0. So, okay, I got all those different projections. It looks kind of like a mess here. But remember what we're doing. We're adding these together. So let's see what happens when I add all these up. All right, let's add all these together, and what do we get? Well, looky there. We actually get a really good approximation to our function. Look at that. Let's zoom in and see how good it is. It's oscillating around it a little bit. I mean, I only went to the third term in the Fourier expansion, so I didn't go very far. As we go further and further into that expansion, if that series does converge, this approximation is going to get better and better and better. Now, one thing to point out is our approximation is only good on the interval that we chose. We chose the interval -1 to 1, and that's the only place where this approximation is good, and that looks like that's where the convergence is occurring. Outside of that interval, not even close, right? No convergence out here. This is going up here. The actual function goes somewhere completely different. But within our interval, minus L to L, we see we're getting a really strong convergence towards the original function. And in this case, if you let that series go to infinity, it would actually give us the function exactly. Okay. So this is really important stuff because if you are analyzing sound waves or things like that, what these Fourier coefficients are giving you is it's giving you the frequencies of the sound. It's telling you how much of the sound is behaving like this frequency or like that frequency. And so if you wanted to decompress sound, as we are doing right now, as I'm doing over this video, sound is being compressed by the computer because you don't want to handle the actual sound wave. The computer compresses everything to make the file size small. If we would deliver over Zoom, over internet conferencing, we want to compress the audio. This is exactly how they do it. They use Fourier expansions to pick out those. They only need a few of those coefficients to get the frequencies that are important. And then they piece those frequencies back together on the other end just by sending just a little bit of data, just those little coefficients, and they can piece together a nice reproduction of the actual sound wave. It's not perfect, but they reproduce the parts that mattered. So picking off these Fourier coefficients allows us to do audio compression and audio analysis of all kinds. So it's incredibly important in that field. Anyway, I've rambled on enough. The beginning of Fourier expansions.